Okay, so over there in the back, that's
Is a
Pythagorean
Pythagorean.
and geometry.
Geometry.
Okay, amazing. Right there with the four equations that you see there. Reverse delta times E, and then vector multiplication, the second one, and so on. Those are the Maxwell equations of electromagnetism. These four equations is the basis of my work. So I use Maxwell's equation. That's really the foundation of my work. These four ones, okay? It's about electromagnetism. Those are atomic weights of elements. If this is the relationship for waves, so the wavelength, you can see it, is at the alpha letter. Beside, I don't know if you see an H over P over there.
Yeah.
Okay. H is the constant Planck.
Is
the
this
Planck
one?
constant.
Is this one?
Yeah. H is the Planck constant. It's the smallest element possible. It's the smallest size in the universe possible. It's a constant called Planck, in the name of Planck, who came up with it. And if you look at the long equation there, towards the right at the bottom,
this one.
there's one that looks like a knife. It has a straight line and a ring like this. Okay. This represents actually the wave function. I work with that as well. The wave function is what determines basically the behavior of particle. And you see those strange design where you have two straight lines with a zigzag in the middle. Okay, and these lines are Feynman diagrams. So remember, they were driving Richard Feynman's van and it blew up. He's the one who came up with these diagrams. That's to represent graphically the interaction between particles. And here you have the standard model. That's the equivalent of the periodic table, but periodic tables for chemistry, atoms for chemistry. This one is for subatomic particles. We call it the standard model.
The square of particles.
Yeah. The particle beam it's 100 meters. And you see all the circuits with the detectors.
And the particles are flowing over there?
Yeah, because the collision happens here. So the particles are expanding like this.
Spinning, okay.
So they go through. This
Through
is just
there
one
and
layer
coming
of
here.
this. Yes. And they're just showing how people are coordinating tasks. So you see who's doing what. Show people how it's done.
Okay. Collision. This is the accelerating cavity. Find out. Okay. Electromagnetic waves are injected into the cavity, which act as a reflector.
Look at the pipes at the top.
Accelerator coming soon. Okay, and the door are extracting a proton accelerator.
The other particle the opposite way.
Okay.
And this is the electromagnet. Voilà.
Ah oui, voilà. Merci. Le tube. Ah, le tube. Oui, ok. D'accord. Ah, mais la sphère ronde.
Exact. Le parking est juste derrière ici.
Voilà. Ok. Alors, ça, c'est le rond-point. Ça, c'est le rond-point en allant vers Meyrin.
So it will come blue, it will attract the red, and then it switches.
Yeah.
You see? So you can only accelerate if you switch quickly enough. So right now blue attracts red, and then you have to switch to post. So the magnet has to switch in a fraction of a second.
The leader. Follow the leader for the tour.
Accelerator we have at CERN, the most powerful accelerator in the world. Okay? So this is an electromagnet. It's used to force the particles.
States, European research is no longer world class. His idea is taken up by American Nobel Prize winner Isidore Radi, who together with Pierre Auger and Eduardo Amaldi convinced UNESCO to adopt this process. Important decisions are taken in the first sessions of the new council. Geneva. Some 54 elements are put together for the magnetic speed. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, a radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the synchrocyclotron is ready, and CERN's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with the target, giving scientists the opportunity to make systematic measurements. Operation of the ESC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the supercyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. Two D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory and they return to the gap after one half turn. Meanwhile, the radio frequency generator reverses the polarity between the two electrodes. The protons are now attracted to the opposite electrode and gain more energy. This process is repeated over and over again. Every time the protons make a half turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin. In 1950, article called the pile. In 1957, there was a mystery surrounding the pile. Theory predicted that a direct decay into an electron and a neutrino should happen, but this had never been observed.
Phenomenology, you see about it. Only
the first pictures show clear evidence for this rare decay.
I'm getting that.
Many important achievements were made, some of them being rewarded with the Nobel Prize. The drift chamber, which revolutionized particle detection, and the Higgs boson, which proves the existence of the Brout-Englert Higgs field. In 1989, Tim Berners-Lee, while working at CERN, created the World Wide Web, which has since changed our world forever. The Large Hadron Collider will continue to run at higher energy and higher intensity, with more than 11,000 scientists from over 100 nationalities hoping for new insights into the secrets of the universe.
I think that
science has grown into a unique model for global scientific and technological collaboration. CERN demonstrates how science can unite nations and contribute to a better world.
So we're back to protons with the energy, and the energy is 14,000 J. So we start from 0.6 J, which corresponds to 80% of the speed of light for a proton. But electrons have they are point-like particles, which is easier to analyze. With protons, we need to this is a lot of mass, we have to filter out to understand what happens at the collision point. Okay? So around the collision point, we have a big detector. So this is one from the left time, the electron accelerator, and this is CMS. So CMS and Atlas are the two bigger detectors, two big experiments around the LHC. There are two other ones which are a bit smaller, but still big, and there are also some very small ones. But the two very big ones, general purpose detectors, and that look at as many mysteries we have in physics as possible.
Dalida.
So this was the
energy field that gives particles their mass. It was the last missing piece of the standard model. This model describes the basic building blocks that make up the world around us. By studying these particles and their interactions, scientists are learning about the structure and fate of our universe.
So the so we think that they will be replaced around 11 by the night shift, and this one will be replaced tomorrow at 7 by the morning shift, because the LHC is always on when it's in operation. So all the people who are here, they are a member of the Atlas collaboration, and this is part of their duties in exchange of being members.
Die Messung ist the main control station.
There's no, since there's no collisions, we're not taking data at the moment. So actually there's not collisions right now, so just being ready, but they're already ready. Collisions, so there they will start to be ready. This is why there is no one. The one just on the left are what we use to visualize the collision. So it's not live because there's no collision at the moment. It's a very long process. It has to be accepted by the collaboration. There are several steps. So you need to make sure the collision So I would say it took about total 1 hour to restart. The average time.
We saw only one of them, but I don't think the other one had anything hot to.
I'm sure they don't have.